Hello and welcome. Today we're going to talk about the language that AI uses to make sense of, well, everything. We're talking about vectors. Now, in machine learning, vectors aren't really about physics. They're the secret code that translates our messy world, everything from national economies to song lyrics, into a language that a computer can finally understand. To kick things off, let's start with a puzzle. Back in 2010, what did the economies of Australia and Mexico have in common? I mean, it's a tough question, right? Where would you even begin to compare two entire countries? Well, you'd probably start with a mountain of data that looks something like this. And this is just a tiny piece of it from the World Bank. You've got GDP, exports, imports, agricultural output, just a massive, messy pile of numbers for 174 different countries. Trying to spot the most similar country in all this? That is a huge, huge challenge, even for a human. But here's the thing. The answer is hiding in there somewhere. And what's so cool is how machine learning finds it. It doesn't get bogged down in all those individual numbers. Nope. It uses this incredible shift in perspective to see the whole picture. It does this. It takes all of that complicated data for a single country and squishes it down into one simple list of numbers. And that list, that's a vector. Think of it like a numerical fingerprint, a digital DNA strand that sums up that country's economy. And this one simple act of translation, well, that's where the real magic begins. So how in the world does this actually work? Let's peel back the first layer, the art of encoding. This is all about the process of turning pretty much anything into one of these super powerful vectors. At its heart, a vector in machine learning is really just a list of numbers that represents the key features of something. So for our country data, the features were things like GDP and exports. But a vector could just as easily represent the pixels in a photo, the words in a book, or even your listening habits on Spotify. It's like a universal translator for data. Okay, so we've turned everything into these neat lists of numbers. Now what? Well, the real power comes from what we do with them next. We're about to enter what's called a vector space. And you can think of it as a playground where this data really comes to life. And this is where that big perspective shift happens. See, that list of numbers isn't just a list anymore. It becomes a coordinate, a single point floating in a high-dimensional space. If our vector has two numbers, it's just a dot on a 2D graph. Easy. But if it has 5 numbers, like our country data, it's a point in a 5-dimensional space. We literally can't picture that. But a computer? It can navigate it perfectly. And inside this space, we've got tools to move these points around. These tools are called linear transformations, and they look like these grids of numbers called matrices. But don't get hung up on the formulas. Just think of them as actions. A rotation matrix can spin all our data points around. A shear matrix can kind of slant them, turning a square into a parallelogram. The point is, we're not just doing abstract math. We are, in a sense, physically moving, stretching, and squashing this entire cloud of data points. So why are we doing this? We're trying to find its underlying shape, to see how the points clump together, and to uncover the patterns that were hidden before. And that brings us to maybe the most critical idea in all of this. Now that our data has a shape, how do we measure it? How do we figure out which of these points are close to each other? The answer, it turns out, really depends on the question you're asking. You see, there are 2 main ways to measure distance here. First, there's Euclidean distance. That's the one we all learned in school. It's just the straight line distance between 2 points. It cares about the raw numbers, the sheer magnitude of the data. But then there's cosine similarity. It completely ignores distance and only measures the angle between 2 vectors. It only cares about direction and proportion. And this one little difference, it changes absolutely everything. So let's go back to our original puzzle. If we ask the computer, hey, find the country closest to Australia using Euclidean distance, meaning the one with the most similar raw economic numbers, the answer it gives us is Mexico. Their GDP, imports, exports, they were closest in sheer size. But now, get this. If we ask the exact same computer to find the country closest to Australia using cosine similarity, caring only about the proportions of their economy, the answer is Colombia. And that right there, that's the aha moment. Same data, different question, totally different result. So what's going on? It's simple, really. Euclidean distance found a country with a similarly sized economy. But cosine similarity found a country with a similarly structured economy. The ratio of exports to GDP, for instance, was more alike between Australia and Colombia. One is about magnitude, the other is about direction. Neither one is wrong, they're just answering two different questions.
Okay, but we can take this even one step further. What if we don't know which features are the most important? What if we want the computer to just find the most important patterns all on its own? For that, we use an incredibly powerful technique called Principal Component Analysis, or PCA.
Now, the official definition sounds pretty intense, right? It's talking about creating a new coordinate system to capture the greatest variance. But don't worry about the jargon, because the core idea is actually super intuitive.
Just imagine all our data is a big, messy, cigar-shaped cloud of points. PCA just does one simple thing. It finds the direction that cloud is most stretched out. That becomes our new main axis, principal component 1. Then it finds the next most stretched out direction that's at a right angle to the first one. That's PC2. It's like finding the main highways in a huge city of data, letting us simplify the map without losing the most important roads. This picture from a linear algebra textbook is the perfect way to think about it. You've got this complex, high-dimensional shape full of data. PCA is just the process of finding the most important flat planes, the most meaningful slices that cut right through that data. It lets us see the hidden structure by throwing away the noise and keeping only what really matters.
So why does all this matter? I mean, this isn't just some abstract math exercise. This idea of turning information into vectors and navigating vector space is the engine that powers so much of the technology that you and I use every single day.
Every time you search for something on Google, your question and all those web pages are turned into vectors to find the closest match. Recommendation engines, whether it's for movies or music, represent you and the items as vectors to find stuff you'll love. It's being used in neuroscience to analyze brain scans, in computer vision to recognize hand gestures, and, as we saw, in economics to model entire countries.
This ability to turn absolutely anything, a piece of music, a medical image, a financial report, into a single point in a shared space is nothing short of revolutionary. It means we can start to measure the distance between things that seem completely unrelated. So it leaves us with this one big question. If anything can be a vector, what hidden connections are we only just beginning to find?